Hello everyone and welcome back. Let's wrap up our mini-series on function hooking and finalize the hijacking of our cool random number generator. Go check out the previous episodes if you haven't seen them already. So far, we've seen how to inject DLLs into other programs and then hook simple functions like, for example, message box from user32.dll. We've then built an application which uses a cryptographically secure function, cryptGetRandom, to generate random numbers. In this part, we'll put these two ideas together and figure out how to alter the random number generation process. And remember, it started with this very useful registry key, app_init_dlls. I will first recompile the second application we wrote. If you remember, we've added a call to message box in order to trigger the linking with user32 library. This requirement comes from app_init_dll's functionality. Let's check out the function hooking library. A lot of the code is similar with what we've seen in the previous episode. Here, I've defined the function that I want to use to replace cryptGenRandom with. The function has the same parameters. First is the cryptographic provider, then a length and a byte array having that length. Our replacement function is very simple. It will populate each element of the array with the number 42. Not very random anymore, right? The next function is unchanged. It's used to decide when the hooking will happen, in this case only for a process named myrandv2. We don't want to mess with the other applications and raise too many red flags. Then we defined the hook function similarly with the previous code. If all the imports from NT-hook engine are okay, we obtain the original address of cryptGetRandom function from adv API32 library. Then we simply replaced it with the function defined before. Next is the code to unhook. We'll keep this here for now. Then a message box prompt to make sure we've reached this part of the code and that we've performed both the hook and unhook. Let's compile and run this code to see how it works and if we need to make any changes. Okay, the library was successfully attached to the process. That's the message box over here. We're here and we should take the interesting process branch. The name of the process matched. The function was also unhooked and some real random numbers were printed. Note that the hooking was not persistent. As soon as we called the unhook API, the original cryptGenRandom function was restored. To continue, let's comment that code. We don't need the unhook part. Let's recompile and rerun. The expected message prompts, but something unexpected happens. The crash reporting process is started. This app is launched automatically by Windows when there's a fault in another application. This is never a good sign, and next we'll see that we probably had a crash and some options to go ahead. One possibility is to go on and debug the crash. We could also send a crash report. Debugging could be tedious, so let's try something else. We'll go step by step through the code and try to see what's happening, what could generate the crash. I will open the binary in IDA Pro. Okay. Let's look at the strings window. search for the main function. This is our message. So this right here is the main function. Let's rename it as such. Looking at the code, here we have the acquisition of the cryptographic context. Straight away, we have the crypto_random function call. What's this? Double click. Looks like this is the crypt_random function from the Windows DLL, Advanced API 32 DLL. Let's debug this and see if we can reach our custom version, and if not, why not? We'll stop before the call we want to debug. But instead of calling or stepping over, just do F7 to step into it. Notice straight away that there's a jump. Most probably this is the code modified by the hooking engine. There's the location of the jump here in the D word. In parallel, let's also examine the original unhooked function. It's in Advanced API 32 library. OK, save the IDA database on the desktop. Then we'll check the exported functions. If you look here, this one jumps to another function with the same name. From cryptsp library. Let's follow this, see where it takes us. OK. It should be located in the same folder, System32. Save the database on the desktop where we have permissions. We don't need the debugging symbols. Go into the exports and then search for crypt_random. This is the true function body of the function we want to replace. Looks very different. In our hooked code, we just had a jump to another function, this one over here, 7504 1000 hex. What does this mean? In which segment is this address located? Use segments window. Our address starts with 7504. There is no segment at that address. One block ends at 74E2 and the next one starts at 7506. There's our problem. No memory segment at that address. Let's continue the debugging and see what happens. The memory could not be executed. Having the previous information about segments, that's expected. Let's have a look at all the libraries that were loaded by the process and their addresses. In the bottom pane of IDA, where we have the messages, we can see the base addresses where each library was loaded at. Search here for 7504. Our custom hijacking library, windows.dll, was loaded at this address. Pause for a moment to think about this. What happened? You also probably spotted that the library was unloaded too. So, first the library is loaded into the memory of our program. That's fine and expected so far. But then it was quickly unloaded. Even though we didn't unhook the function, the library was ejected by the operating system from memory. Why? If we head over to MSDN and read the documentation on DLL main function, things will start to make sense. That explains the events when a library is attached to a process. We enter this switch branch, this code over here executes, and it will call the hook function, which was successful. We got the message. Function will then return false and terminate. What this return code means, and again check MSDN, is that the library will be quickly unloaded by the operating system. If DLL main returns false, the OS will immediately call the entry point again with DLL process detach and unload the library. So we need to make sure we return true after the DLL is attached. A minor detail overlooked when I copy-pasted the function boilerplate, but the debugging experience taught us a few things about how to troubleshoot library loading. Let's recompile the library and retest. We can't open windows.dll, no problem. Just delete it, compile again, and start debugging. When we reach crypt-gen-random, step into the function. The address now is slightly different, but this doesn't matter. Press F7. We have reached our custom hook function. Notice the message box with our text over here. Great! Let's run the application outside the debugger in a terminal and verify the output. We were finally able to hijack the random number generator. We're getting closer to the end of our short journey into library hijacking and function hooking. I hope you enjoyed the debugging and troubleshooting tips and you'll apply them in your investigations. If you're interested in the topic, there are plenty more resources out there about library hijacking, and this is a fun topic to dive into. This technique has many other applications way beyond the use case we've discussed in this episode. I'll post a link to the source code and previous parts in the notes. Waiting for your comments and feedback. Thank you very much for watching and see you in the next episode. Cheers!